Next up is what we call extensive form game. Realistically, sometimes there are clear order of movement, right? There's rarely do you actually move at the same time, unless you're playing rock, paper, and scissors, right? Otherwise, you usually move in turns. So now suppose Mary gets to decide which movie to see before David does. Ladies first. What would happen? Which one should Mary choose? Should she choose one from the two at random? Remember, there are two possible stable outcomes, right? Basically, the criterion is that they both go to see the same movie. And there are two movies, so there are two stable outcomes. They can both go to the action movie, or they can both go to the romance movie. Now, the question in concern is, if Mary gets to move first, which one should she go? Now, intuitively, if you know your friend is going to go to the same movie as you do, and you get to choose which one to go, which one will you choose? Obviously, you're going to choose one that you like, right? So, in this case, that you would think that that's what Mary should do, right? She should choose the romance movie that she likes, and with the understanding that David is going to follow her. So once Mary has chosen romance movie, based on what we have talked about before, once Mary has chosen the romance movie, the game basically simplifies to these two possibilities. David choosing action movie, going alone, versus choosing romance movie, going with Mary. And we already know that's what he's going to choose. Now, it might be more clear if we represent the game in a tree diagram. So now it makes it very clear who gets to move first. You read the diagram from top to bottom. Mary moved first. She gets to choose A representing action movie and R representing the romance movie. Now, depending on what Mary chooses, you are in a very different state of the world, right? In one case, this David here, on the left-hand side, this David lives in a world where Mary has already chosen the action movie. On the right-hand side, you have another David. This David lives in the world where Mary has already chosen romance. These two David are facing different decisions, right? So, if Mary has chosen the action movie, David would choose the action movie, as we can see from the payoff here. And if Mary has chosen the romance movie, David would choose the romance movie, as we see from the payoffs here, right? So, depending on what Mary does, David would, in one case, choose the action movie, and the other case, choose the romance movie. Now, in game theory, one of the defining features is that we assume people understand this dynamics. When I make a decision and you make a decision after me, I can predict your reaction accurately, right? When I do something and you react, I can predict your reaction accurately. So in this case, Mary understands that her action would lead to David choosing something different, right? Mary understands what's happening here. Mary is as smart as we are. In fact, she might be smarter than us, as we will talk about later on. So she understands this dynamics. She understands that if she goes to the left-hand side, choosing action movie, David would respond by choosing the action movie. And if she moves to the right-hand side, choosing the romance movie, David would respond by choosing the romance movie. That means she understands that her choice would lead to the following two outcomes. She understands that her choice would lead to either she getting 1 by choosing the action movie, or getting, so this, okay, the red line is actually not in the correct position. The red line is here, okay. So Mary understands that she's either getting 1 if she chooses the romance movie, or she's getting 2 if she chooses the if she's getting 1 if you choose the action movie, and getting 2 if you choose the romance movie. And 2 is bigger than 1. So she's going to choose the romance movie. So what you need to remember is that because of this process where players can predict what other players do, to solve the game, you practically have to start from the back. The way we did it, you can see that we moved backwards from the game. Mary moved first, David moved second. But we solved the game by first asking what David would do in each scenario. And then we moved backwards, figuring out what Mary would do, given her prediction of what David would do. Right? So this method of solving the game is called backward induction. Okay, backward induction. I think it's on the next slide. Okay, so this is just repeating what I said. Extensive form game has to be solved from the back. You first figure out what David would do in this case for every possible action. Now I have to emphasize this, is that you have to solve for every possible action. Okay. So you can think about it this way, right? There are 2 possible states of the world. By now, we understand that only the right one would appear. However, as a rule, when you solve the game, you have to solve it for every possible scenario, including ones that would never happen. In this case, we have the left case and the right case. The left case never happens, because Mary would never choose the action movie, but still, you have to figure out what David would do. Well, I will explain in a moment why. And Mary, so you solve, in this case, you can solve, let me say 1, 2, you solve these 2 cases, and then you move 1 step up and ask what Mary would do. This is number 3. So see the way it works? Solve the bottom, 1, 2, and then go back up. This is the 3rd case you have to solve. So this is called backward induction. So the process works the same way, no matter how big the game is. So in the assignment, you will see that the games could be 3 or 4 or 5 layers deep. Obviously, if it's 5 layers deep, the game has to be relatively simple for you to be able to actually figure it out. But the way of solving is the same. Even if it's 5 or 6 layers deep, you still start. The equilibrium concept in an extensive form game is called subgame perfect equilibrium. It sounds very technical, but it's actually quite intuitive in what it means. All right, what is subgame? Subgame refers to each individual tree knot, right? So each one of these are subgame. This is a subgame. The right hand side is also subgame, and the overall is a subgame, right? Each bracket is a subgame. Each individual tree knot is a subgame. The overall game is also a subgame. What is perfect? Perfect means that the players are required to pick the optimal action in every single subgame. What does that mean? Take a look in these cases. The right-hand side is the easy case. On the right-hand side, Mary chooses romance movie. David responds by choosing the romance movie, because that's the best he can do. The left-hand side, Mary chooses the action movie, David is also going to choose the action movie. That's the best he can do in that scenario, right? Given that Mary has chosen an action movie, the best David could do is an action movie. Given that Mary has chosen a romance movie, the best David could do is a romance movie. That's the best he could do, given the scenario. And finally, Mary's best action, given the overall situation, is the romance movie. So in each step, they are picking the best possible action, given the constraint they are facing. So that's perfect, right? What does that rule out? That rules out incredible threats. This is important because it has big consequences. Suppose you allow David to do something weird, right? Let's say David does not need to choose the best possible options given the constraint. In particular, let's say even if Mary chooses the romance movie, David, in contrary to his payoff, he chooses action, right? Movie, right? It's against his payoff, but let's say we allow him to do that. That would not be perfect because he's choosing something that is not in his best interest in that particular moment. But let's say we allow him to do that. What would happen? Now, so let me use the blue color to, I'm going to use the blue color to represent this possibility, right? Okay, let's say this is what happens. We allow David to say, I'm always going to do the action movie, regardless of my payoff. What would Mary do if Mary follows the rules? He's going to choose the action movie, right? Because given what David is going to do, if she chooses a romance movie, now she's going to end up with 0. So incredible threats would lead to different outcomes. Right? So think about this, right? Let's say you have a mother forcing her child to do homework, right? The child threatens that he's going to jump off the cliff, jump off the building if she forces her to do homework, right? Do you believe in her? Usually when children make such threats, it's empty threats. They're not actually going to jump off a cliff. So, from that perspective, you would say that mother doesn't need taking that into consideration. But if you truly believe that the child is going to jump off the building, then you would want to change your action. You won't want to force her to do homework, right? So, allowing empty threats would change the outcome of a game. In a subgame perfect equilibrium, this is not allowed. You cannot make empty threats. Whatever you say, you do, right? So this is important because you might think that empty threats do happen in real world. Yet in this particular concept of equilibrium, it does not happen. People do not make empty threats. Whatever they say, they mean it. That's a requirement of the game. Okay? That's a requirement of the game. So when you write down the strategy, for David, because his plan involves, and some sort, you can say its plan involves multiple possibilities. Here we go. When you write out the solution, in this case, David's strategy depends on David's strategy depends on what Mary actually chooses. So his plan is contingent on what Mary would do. So if Mary chooses A, David is going to choose A, and if Mary chooses R, David is going to choose R. So what he does depends on what Mary does. This is his strategy. His strategy is contingent on Mary's action. Mary's strategy is a single action because she is the one who moves this first. So in her case, she's simply going to choose R. Right? So that's the subgame perfect equilibrium. Mary always chooses R, and David chooses R if Mary chooses R, and A if Mary chooses A. Once again, we have to specify what David would do even for cases that never happens. Right. Is that realistic? Probably not, but but this is the way it works in game theory. We'll talk more about whether this is realistic in a moment, but probably not. Notice that in this particular case, Mary is better off, right? Mary gets to choose, essentially. She understands that David is going to follow her, so she chooses what she wants. That's called a first mover advantage. In this particular case, only romance is the equilibrium, right? Action is not an equilibrium outcome. Mary is never going to choose an action movie, so it never occurs that both of them go to the action movie. Whereas if they move simultaneously, you can imagine that in some cases, Mary and David would choose the same movie action. So you can say that by moving first, Mary picks the outcome that is better for her. That's called a first mover advantage. When there are more than one Nash equilibria, the player who moves first can pick the one that gives her the highest payoff. Right. So it seems like it's always better to move first. Well, not necessarily true, as we'll see in the next example, I think. It's not necessarily better. So we'll see in a moment. But in this particular case, when there are different stable Nash equilibria, by moving first, you can pick the ones that benefits you the most. Okay, now back to whether it's realistic. So extensive form game made at least 3 contestable assumptions. One is this, what we call hyper-rationality. Players are capable of doing this mental process of predicting what the other players would do for even very long games. In this course, we only deal with games that are at most like 3 layers deep. We never deal with games that are really, really deep. But theoretically, when you face such a game, the process is the same. The players are capable of playing out the whole game to make a prediction of what the other players are going to do. So that's why it's called hyper-rationality, because think about it. If you need to play out a game that long, it's a very tedious mental process, which is probably not humanly possible. Any of you play chess games, like Chinese chess or just Western chess? If you play a chess game, now you understand that it's beneficial to be able to think ahead, right? To be able to predict what your opponent is going to do in the game. But if you play a chess game, you understand that in terms of human capabilities, it's impossible for you to mentally play out the whole game in your mind. You might be able to do a few steps ahead, or for really good players, maybe a dozen of steps. But it's probably impossible to think like 100 steps ahead. You need to use some sort of heuristics, right? For games as simple as tit for tat, maybe we can do it, but not for chess. In fact, if you pay attention to news recently, you know that we have this supercomputer AlphaGo beating human like Zero on Go, right? So even a supercomputer cannot actually solve the game of Go completely. It's just impossible because the number of possibilities in a game of Go is too large. Now, a game of Go is simply a part of your life, right? A game of Go involves something like, I believe it's like, what? How many possibilities? Something like 2 to the 170, I don't know. So it involves too many possibilities. And think about your real life, it involves even more possibilities. And so it's unrealistic to assume that people can actually work out all possible future outcomes. But this is what required in game theory. So remember, this is unrealistic. Second, complete plan. Players have plans for every state of the game, including outcomes that do not occur. Is that realistic? Simple. What's your plan? What's your plan if there's an earthquake in Hong Kong in the next 30 seconds? Plan? None, right? No plan. Now, that you already violated a complete plan. Is the chance of having an earthquake in Hong Kong in the next 30 seconds 0? No. It actually has some chance, right? But no one has a plan for that because it's just too unlikely to warrant the effort to form a plan. So having a complete plan for every state of the world, including ones that never happen, is not realistic. But once again, it's a requirement in game theory here. Okay? It's required in a subgame perfect equilibrium. It's unrealistic. Finally, I've already mentioned that just a moment ago, is that the plan has to be optimal. What player plans do have to be optimal within each subgame, but as we already mentioned, people routinely make empty threats, right? People routinely make empty threats. Children threaten to jump off a building. Like couples threaten to break up, right? So empty threats happens in the real world are not allowed in the subgame perfect equilibrium, which once again remove a degree of reality, but in turn what we get is a simpler solution, right? If you have to consider all the nuances of human behavior, you would not get a simple solution. It would be a complicated solution. So by assuming these three things, we get a simple solution. People do what's optimal for them. Okay. So I'm going to start with the normal form, right? Okay. What would small potato do if Superman Lee accommodate its entrant? Well, if small potato stays out, he gets 0 because he's not entering, so he's not gaining money, he's not losing money. If he comes in, he's going to be able to capture market share from Superman Lee. So he's going to get 2 instead of 0, so he wants to come in. In the case that Superman Lee fights, small potato coming in would lose money. He would rather stay out, right? So what small potato will do depends on what Superman Lee does. Now let's think about what happens if given that small potato is coming in for sure. That's 3. Right. If small potato is coming in for sure, Superman Lee has a choice of accommodating and fighting, and it doesn't matter because small potato is not entering, so the market is the same regardless of whether he fights or accommodates. So he doesn't really care so much. So it's both are possible cases. And in the case that small potato comes in, Superman Lee has these 2 choices. Accommodating, which means less profit, but not losing money, and fighting, which means losing money, because this is a price war, so he's going to lose money by fighting. So he's rather not going to fight. Right. So, in the end, you have these 2 possibilities. One is small potato comes in, Superman Lee accommodates, or the other case is Superman Lee fights and small potato stay out, right? It makes a lot of sense naturally, right? You have these 2 possible competitors. One possibility is the existing competitor threatens to fight, scaring the potential entrant away. The other possibility is the potential entrant comes in anyway, and then it's going to win because it has lower cost. So these two sound natural outcomes, right? In this case, fighting doesn't actual fighting doesn't happen, right? Only the threat of fighting would be enough, because fighting is costly to both parties, so they would rather not actually fighting. What about, so just before I continue, let me write down possible outcomes, right? So Nash equilibrium would be small potato coming in, supermanly accommodate, and small potato staying out and supermanly fight. Understanding that there is actually no fighting, it's more like a posture to fight. What about a subgame perfect equilibrium? In a subgame perfect equilibrium, you start from the back. If supermanly, well, okay, so in this case, the order is important, because in here, I assume that small potato move first. You can argue that maybe supermanly should move first, because he is the existing seller. Maybe he can like pose to fight before small potato actually decides whether to enter. Yes, that's fine. That's possible. That's another game you can try. In this particular case, I assume small potato moved first for no particular reason. It's just an example. So if small potato gets to decide first, what would supermanly do? Supermanly is facing a choice between, have the same numbers as before. He's facing a choice between fighting and accommodating. And as we know, accommodating is the better choice in this case. So he's going to choose this. He's going to choose accommodating because 1 is better than -1, right? 1 is better than -1. Now, small potato now faces a choice between staying out and getting 0 and coming in and getting 2, right? We now know that supermanly is going to accommodate if small potato actually enters. So it's a comparison between getting 0 and getting 2, and getting 2 is better. So we know that small potato is going to come in, right? He's going to come in because he now understands that if he comes in, supermanly is definitely going to accommodate, which is something he cannot assume when they move together, right? So the subgame perfect equilibrium in this case, once again, you have to write out the strategy, is so small, I'm just going to skip the bracket since the bracket is very hard to draw nicely in here. Small potato is going to come in, whereas supermanly is going to accommodate. Now, here's actually interesting part is that we don't actually, I didn't actually specify what supermanly is going to do if small potato stays out, right? Small potato stays out. Because in this particular case, the payoff is the same, so I didn't actually specify. I'm just going to assume he's going to accommodate anyway, because it doesn't actually, right, doesn't matter. I think that maybe it actually matters, right? If it stays out, yeah, fighting and accommodate is actually the same, yeah, so it's actually willing to do both. So I'm just going to assume he's going to accommodate. Right. So in this case, there's only one possibility, right? When they move together, there are 2 possibilities, but when they move in turns, then only one is possible. You can imagine that if you flip the order of movement, if supermanly gets to move first, you would end up with fighting and out, right? Because this is the first mover advantage. When whoever moves first gets to pick. Okay. Try this game. This is a normal form game. Take a look, or you can try actually drawing circles. See if you can find a pure strategy Nash equilibrium. This game is called matching pennies. Do you find any stable outcome? The answer should be none, right? Okay, let me just illustrate, right? Now this game is called matching pennies because player 1 and player 2 are supposed to be playing a game where each one of them put forward a side of the coin, right? The penny. Player 1 wins by matching the side of player 2, but player 2 wins by mismatching the side of player 1. So you can naturally imagine that there simply cannot be an agreement of what to do. I win by matching your coin. You win by mismatching my coin. If I win, you lose. If you win, I lose. So there's no stable outcome. And let's show that here. Let's say player 2 decide to put forward a head. Player 1 wins by matching that side. So he would want to put forward a head too, right? What if player 2 put forward a tail? Well, player 1 wins by matching player 2's coin, so he's going to put forward a tail. Good. What about what if player 1 put forward a head? What would player 2 wants to do? Player 2 wins by mismatching. So if player 1 put a head out, then player 2 wants to put a tail. So as you can see, in this case, 1 versus -1. So player 2 is going to put forward a tail. Finally, if player 1 is put forward a tail, player 2 wins by mismatching, so she's going to put forward a head. So, as you can see in this particular case, there is no stable equilibrium. None. Because the two players' incentives are intentionally opposite of each other. Any dominant strategy, remember, dominant strategy is one that is an action that you always take. Dominated strategy is an action that you never take. None here, right? Your action depends on what the other player does, and you want to use all possible actions depending on the situation. So none and none. All right. So why do I want to mention this particular example? In some sense, this is a simplified example. This is a simplified version of rock, paper, and scissors. In rock, paper, and scissors, there are 3 possibilities. Here there are 2, but it's the same idea, right? In rock, paper, and scissors, do you ever settle on a single action? Like, think about it, right? Let's say if I play rock, paper, and scissors with you, and I tell you I always use rock, what would you do? You always use paper, right? You always win. But what would I want to do given that you use paper? I want to use scissors. If I always use scissors, what do you want to do? You want to use rock. If you use rock, I'll use paper. If I use paper, you use scissors. And you use scissors, I use rock. In rock, paper, and scissors, you never use a single action. That's a guaranteed way of losing. So this is a simplified version of that, right? If player 1 always put forward a hat, player 2 can guarantee a win by putting forward a tail. In that case, player 1 wants to put tail, and player 2 wants to put hat. Then what? Does that mean there is no concept of stability? No. what we get out of this is that pure strategy Nash equilibrium does not always exist. In many situations, picking a single action is not feasible. What happens? Once again, it's best to think about what happens in rock, paper, and scissors. What do you do? Right. In playing rock, paper, and scissors, it should be randomizing, right? That's what you do. You don't use a single action, you randomize between rock, paper, and scissors. Now, if you think about it, in some sense, that could be another form of stability. You randomize, you are intentionally deciding that you can randomize between the three possible actions. So, when players cannot choose a single action, they randomize among different actions. And this leads to the concept of mixed strategy Nash equilibrium. Instead of choosing a single action, each player chooses a probability to randomize among different actions. Given the probabilities other players have chosen, each player has no incentive to change their probability. So we change the stability concept. Instead of saying a single action being chosen, we say a probability is being chosen. So that's still stability, because as long as the players can agree on us choosing a probability. So I'm going to choose one half heads, 1/2 tails. I'm always going to put forward half heads, half tails. That's stable probability. The action is random, but the probability is stable. What would not be stable is sometimes I decide, okay, I'm going to have this time there's a 1/3 chance I'm going to put forward a head. Next time I have a 2/3 chance of putting forward a head. That's not stable. But as long as the player has decided, I have a half chance of putting forward a head and half chance of putting forward a tail, that's stable probability. And that's what defines stability in mixed strategy Nash equilibrium. You pick a probability, I pick a probability. Given your probability, I don't want to change my probability. And given my probability, you don't want to change your probability. That's stable. And now we have to think about why it's actually possible, right? Does it actually happen that we pick stable probabilities? So in fact, theoretically, it's always possible. A mixed strategy Nash equilibrium always exists. Now, pure strategy Nash equilibrium is a special case of mixed strategy, because pure strategy is the same as saying you are choosing a particular action with probability 1, right? And probability 1 is still a probability. So pure strategy is a special case. If you include pure strategy Nash equilibrium, then you always have a mixed strategy. In any scenario you can think of, a certain randomization technique will always guarantee that we will want to stick with what we are currently doing. Okay. So to show that how this works, let's use rock, paper, and scissors again. Now this is the case I've already mentioned, right? If I always use rock, you always use paper. You win 100% of the time. So that's a simple case. Let me give you a more complicated. Okay, let me give you a more complicated case. Okay. What if I use rock 80% of the time? What will you do? What will you do? Should you use paper 80% of the time? No. What should you do? Now remember, you don't actually know when I'm going to use rock, right? You only know that of all the rounds we play, 80% of the rounds, I will use rock. How do you maximize your chance of winning? You should always use paper. Because you don't know when I'm going to exactly use rock, you do know that I'm overall 80% chance you're going to meet, 80% of the time you're going to see a rock from me. By using paper all the time, you guarantee that you win 80% of the time. That's the best you can do. You can try calculating out the probabilities, but this is the best we can do. winning 80% of the time. Right, this is even harder. I use rock 40% of the time, paper and scissors each 30%. What should you do? Once again, you don't know when I'm going to use each particular type. All you know is I'm randomizing, but you will see 40%. You will see rock 40% of the time. What should you do? What maximizes your chance of winning? Now you can try to calculate the probability. Once again, if you like, you can actually calculate the probabilities, but by the same logic as before, you should always use paper because it gives you a slight edge, and you win 40% of the time if you stick with paper. Right? You can try calculating it, but I can guarantee you this is going to be the case. It makes sense if you think about it. Based on the fact that you cannot predict what I'm going to do in a particular round. If you use anything other than paper, sometimes you win, sometimes you lose, sometimes you draw. Right? But if you always use paper, you're guaranteed to win 40% of the time. Right? Which is better than pure luck. Definitely. Right? So the observation here is that you do not necessarily want to randomize just because I'm randomizing. It's actually, in some sense, more difficult than we assume. In playing rock, paper, and scissors, it's not immediately obvious that you want to use all three possible actions. I've just shown you that in many, many cases, you want to use just a single type of action. In what case would you actually want to randomize? Now, you only want to randomize if randomizing doesn't make you less likely to win, right? In all these cases, I've argued that by using paper, you raise your chance of winning. So, in order for you to be able to be willing to randomize, it must be the case that randomizing doesn't lower your chance of winning. Right? In what case would your chance of winning be the same regardless of what you do? Right? You need a situation where it doesn't favor a particular type of action. And naturally, what would that be? Naturally, that would be the case when your opponent uses rock, paper, and scissors 1/3 of the time each. Right? In that case, in every single action you use, rock, paper, or scissors, they all give you the same chance of winning, which is 1/3 chance of winning, 1/3 chance of losing, and 1/3 chance of a draw. If your opponent deviates from that pattern, even just by like 1% chance, you're better off switching to the counter strategy that always guarantees you a high chance of winning, right? If I just use rock 1% more often than usual, it benefits you to use paper always, right? So the key observation here is that for you to randomize, actually I must be randomizing in a particular way. And this is the key in how we figure out the numbers in the solution. For you to randomize, I have to be randomizing in a particular way. Or put it another way, for your actions to give you the same payoff, my probability has to be a particular number. Right? Your payoff means that I have a particular probability. So conversely, my payoff means that your probability is a particular number. So that's how we can calculate it in a moment. Right. So to solve a mixed strategy Nash equilibrium, you have to equalize the payoff of player 1 to find the probability of player 2. Right? So if player 1 if player 1 chooses action A with probability P, okay, and player 2 chooses action C with a probability Q, if you want to find Q, which is the probability adopted by player 2, you actually have to equalize the payoff of player 1. Why equalize payoff? Equalize payoff means you don't care which action you use, so you're willing to randomize. Okay, so same payoff means willing to randomize. Because I already mentioned in the previous examples, right? If the payoffs are not the same, you would want to switch to the actions that give you the highest payoff. So for you to be willing to randomize, it must be the case that all the actions give you the same payoff. And this happens only if I am doing something in particular. So we use your payoff to find my probability. Right. So because it's random, we have to calculate the average payoff. So this is called expected payoff. So it's just the average, right? Average. So expected payoff from player 1 using action A has to equal to the expected payoff from player 1 choosing action B. Expected payoff is simply the average. So it's simply the average. Okay? So the average depends on the chance of something happening, and that's Q. So player 2 has a Q chance of taking action C. If player 2 chooses action C and player 1 takes action A, player 1's payoff is 1. Okay, so right, so just to make it very clear, you have probability of action C multiplied by the payoff, right? Payoff of AC plus probability of D multiplied by the payoff of AD. Okay? That has to equal what happens if player 2 chooses action C and player 1 chooses action B plus probability of action D times the payoff of B and D for player 1. Okay? So average payoff. Average payoff. The probability of C is Q. So Q, what is the payoff of AC for player 1? It's 1. Right? Plus, what's the chance of D? D means not C. So D would have 1 minus Q chance. Okay? And what does player 1 get in this case? -1. Right? To make it easier for you to see, I'm going to use color code, right? In this moment. 1, -1. Right? Okay. What happens if player 1 chooses action B? Q chance, we're going to end up in a situation where player 1 chooses B, player 2 chooses C, and 1 minus Q chance, we're going to end up in a situation where player 1 chooses B, player 2 chooses D. So I'm going to use blue in this case. So if if player 1 chooses B, player 2 chooses C, player 1 is going to get -1. And if player 1 chooses B and player 2 chooses D, you're going to end up with 1 for player 1. So with these numbers, and if you rearrange, you would get Q equals to half. So what does that mean? What this means is that for player 1 to be willing to randomize between the two possible actions, it must be the case that player 1 gets the same average payoff no matter what he does. This is only possible if player 2 is choosing her actions half the time. If player 2 is choosing something different, player 1 would not be randomizing. Player 1 would be choosing a particular action because that would maximize the chance of winning. Right? Next, what do you do with player 1? What do you do with finding P? Right? Player 1 has a P chance of using action A, which means he has a 1 minus P chance of using action B. Okay, so very quickly, you would need expected payoff for player 2 from action C equals to expected payoff from action D. Right? So let's make this calculation. If player 1 uses action A and player 2 uses action C, what does she get? Okay, let me use green. She gets -1. Right? And then if player 1 chooses action B, which happens in 1 minus P case, and player 2 chooses action C, okay, then we have 1. Right. Now we go to the other case. If player 1 uses action A, player 2 chooses action D. We are on the top right corner, and I'm going to use purple. Purple. Player 2 is going to get 1. And finally, if player 1 chooses action B, which happens 1 minus P chance, and player 2 chooses action D, she is going to get -1. All right? Still following what I'm doing? So once again, the only unknown in this particular exercise is P. So P, if you simplify, you get half. What does that mean? That means for player 2 to be willing to randomize, her payoff must be the same regardless of what she do. Taking action C has to pay the same as action D on average. On average. That only happens if player 1 randomize between her two actions with probability P. Right? What I do affects what you want to do, and what you do affects what I want to do. I must be randomizing in a particular way for you to be willing to randomize. And you must be randomizing in a particular way for me to be willing to randomize. This exercise figures that out. Right? My payoff, equalizing my payoff, guarantees that I'm willing to randomize. From that, we can deduce what probability you must be using. Equalizing your payoff. So let's leave the exercise next time because I want to show you this. In reality, when you play rock, paper, and scissors, do you actually randomize 1/3, 1/3, 1/3 of the time? So there's actually this association of the World Association of Rock, Paper, and Scissors that actually exists. Okay, and sorry that's in Chinese, but what it means is that, okay, how to win rock, paper, and scissors contest. Okay, strategy 1. When you're facing a male, use rock. Right? No, bao is paper, right? Okay, when you're facing a male, use paper. Because study indicates that male like to use rock in the first round. Okay. Strategy 2, use scissors against an old hand, right? Something against an experienced player, use scissors. Because somehow experienced players use paper most of the time, perhaps because of the first reason, I don't know. Strategy 3, novice likes to use whatever the other player has been using, right? So, what you want to do is, you first use rock. What do you do in the second round? You always use paper. You use paper, right? Because the other player is going to mimic what you're going to do. Right. Strategy 4. When someone has repeated himself twice, you can guarantee that he's going to do something opposite. Right? Rock, rock. Okay. What would happen in the third round? He's most likely going to use scissors. Because the logic is, I use rock. I think you are going to think I'm going to use rock again. So I know you know that. So I'm going to use scissors so that I will win against your paper. Right? Hyper rationality. Just I know you know, I know you both you know thing. Right? So finally, I got you 2 more, right? Look at the hand gesture, right? Okay. So if all the fingers are relaxed, then that means paper, right? That if all the fingers are tight, that means a rock, and only 2 fingers are holding each other, that would mean scissors. And finally, somehow using paper has a good high chance of winning, right? High chance of winning. And here's that overall chance. Right? Okay, so the reason is, overall, based on the summary statistics of the World Rock, Paper, and Scissors Society, people overall have a 35.4 chance of pick off using a rock, which therefore means that if you use paper, that gives you the highest chance of winning overall. Right? Remember what I said. If only there is a slight chance of your opponent using a particular strategy more often, you should completely switch to the counter strategy. This is exactly the recommendation. Because there's a 0.4 chance that a given player is going to use rock over the next strategy, scissors. You should always use paper, because that gives you a 0.4 chance of winning. High, right? Okay, so how much of this is just statistical flunk? I don't know. Okay. What I can tell you is, strategy 4 does have very strong psychological support. Is that if you study, if you take a course like I teach a course in the 4,000 level course, 4470 in economics department called the Economics of Behavioral Finance, we talk about psychological findings in terms of people betting, right? And people generally do not like repeating themselves 3 times in a row, right? They definitely want, what they want to do is they understand this concept of 1/3, 1/3, 1/3. When you repeat yourself twice, you are not doing this 1/3, 1/3, 1/3. So they have a very high tendency to do something opposite. This is definitely supported by psychological research. Right. And if we have more chance, we can talk about that. All right, so that's where we're going to stop here today, because the department's TA is here to do the evaluations. We'll still meet here on Wednesday to finish up with game theory, but I think we would be fine. Right? So see you on Wednesday.